Okay, back to PDE. Unfortunately, on Monday, my house lost power and internet, and so we missed that class, and planning to make it up next week. Let's see. Any questions before we start? So let me make the following observation. So, excuse me. In terms of a makeup class, we meet Monday and Wednesday. The easiest thing would also be to meet on Friday morning at this time. How does that sound to you? Well, we'll think about it. And I might actually schedule 2 makeup classes. So if you can't make one, you can make the other. We'll see. So methods to solve PDEs. So there is separation of variables, which we mentioned a little bit. There is what is called the method of characteristics, which is the last thing we did, and I'm going to work some problems today. The use of what is called the Laplace Transform, which I hope I will also introduce today. So I just want to make sure that I've covered these 3 methods before our second midterm, which is so we're looking at what is called a Cauchy problem, after the French mathematician Cauchy, who lived in the 18th century. And this is basically a problem where you have some initial condition with no boundary condition. So a first order Cauchy problem is the type of problem we're considering now, where we have an unknown function u and an equation of the form partial of u with respect to t plus some function called c of xt partial of u with respect to x equals some function f of xt. And some initial condition, which is, let's say, u of x0 is equal to some function capital F of x. So this is the initial condition, and this is the first order PDE. And the simplest case is when c of xt equals c, a constant, and f of xt is 0. So we have this homogeneous equation. U sub t of xt plus c u sub x of xt is equal to 0. And f of x0, sorry, u of x0 is some function f of x. I mean, use a lower, I want this to be the same notation as the function, yes, capital F of x. So one solution is, suppose we take let u of xt be equal to f of x minus ct. No. Let me write this down again over here. So we have the partial differential equation u sub t plus c u sub x equals 0, and u of x0 is some function capital F of x. Suppose we define u of xt to be f of x minus ct. Then the partial of u with respect to x is what? It's the derivative of this at x minus ct times the derivative of x minus ct with respect to x, which is 1. The partial of u with respect to t is f prime, sorry, so the partial of u with respect to t is f prime of x minus ct times the derivative of x minus ct with respect to t, which is minus c. So we see that u sub t plus c u sub x is minus c f prime of x minus ct plus c u sub x is f prime of x minus ct. These cancel, we get 0. So this is a solution. And it tells us the following. Suppose at t equals 0, the graph of the solution is some function. At t equal 1, the graph of the solution is this function translated by c. Let's see. So looks like that. And so for any given time t, u of xt is the initial value of the function f of x0 translated by t. This is sometimes what is called a traveling wave. So capital F of x is the initial condition for the function, f of x0, defined for all x. In this equation, I should always say, this is defined from minus infinity to plus infinity for x, and for positive t greater than or equal to 0. So for t greater than or equal to 0, at every time, what the solution looks like is the initial value of the function translated to the right by the amount ct. So let me try and do some of the homework problems. In fact, I want to do a lot of them. So we can try and see the technique for solving this type of Cauchy problem. So let me start with, so this is in the book by Logan, page 25, number 5. So this is a pure initial value problem. So x is from minus infinity to plus infinity, and t greater than 0. And we have the following partial differential equation, first order. u sub t plus xt u sub x equals 0, and u of x 0 equals some function f of x. So this is the initial condition. So you can think of this as, this is my function c of xt. And what I want to do is to solve the first order differential equation, dx derivative with respect to t of c of xt. That's the derivative with respect to t. Sorry. Excuse me. What I want is dx dt is c of xt. So set dx dt is c of xt, which in this case is t times x, x times t. So let me just write it down simply. Dx dt equals xt. And x at times 0 is, let's say, some number x0. So this is an ordinary differential equation to solve. We can solve this by separation of variables. 1 over x dx dt equals t. So the integral of 1 over x dx equals the integral of t dt, which tells us that the log of x is equal to a half t squared plus some constant. So if we exponentiate, we get x, which is some function of t, it's a curve, is equal to e to the 1/2 t squared times some constant c. And when t is equal to 0, the constant has to be x0. So this is some curve. And what I claim is that u of xt is constant on this curve. So I have this first order partial differential equation, partial of u with respect to t, partial of u with respect to x. It's linear. This is a function of x and t, but not of u. It's homogeneous. This is 0. And the method of characteristics means you're going to find a certain curve, so-called characteristic curve, on which u of xt is constant. I claim u of xt is constant on this function. So what does this mean? This means I look at u evaluated at x of t comma t. And how will I know if it's constant? Well, a constant function has a derivative equal to 0. So let me differentiate this function of t with respect to t. So we know this is the partial of u with respect to x, dx dt, plus the partial of u with respect to t, dt dt. It's the partial of u with respect to x times the derivative of the first variable times the partial of u with respect to t times the derivative of the second variable. So this is u sub x evaluated at x of t comma t. What is dx dt? Dx dt is xt plus u sub t evaluated at x of t comma t times 1. So this is what? This is u sub t plus xt u sub x. That's 0. Okay. If u is a solution of the differential equation, this is 0. So what this means is that u of x of t comma t is constant with respect to t. U of x of 0 comma 0, that's u of x 0 comma 0, well, my initial condition is f, this is f of x 0. So let me just summarize this. For t greater than 0, u of x of t comma t is constant. So therefore, u of x of t comma t is, if it's constant with respect to t, it's u of x of 0 comma 0. X of 0 is just this initial condition, x naught. This is u of x naught comma 0, which is f of x naught. Remember that our differential equation x, which is x of t, was x naught e to the t squared over 2. So x naught is x of t e to the minus t squared over 2. So u of xt is equal to f of x e to the minus t squared over 2. And that is the solution of the differential equation. So recall we had these curves, x of t equals x naught e to the t squared over 2. And this curve, what does this curve look like? At 0, it's equal to x naught. And then it just goes up exponentially. And so for every possible value of x naught, we have this family of exponential curves. The solution of the differential equation is constant on these curves, and it's equal to exactly this. So let me do more problems, because I think the only way to have, I don't know. Let me just keep doing more problems. So this problem 5 had 2 parts. The first part was to solve the homogeneous equation. The second part was to solve the inhomogeneous equation when the right-hand side was equal to t. So let's take a look at that. So this is also number 5. We might call it part B as the second part. We have the differential equation u sub t, sorry, slightly different, plus x u sub x equals e to the t. And the initial condition is that at time 0, u of x 0 is f of x. So f of x is just the initial condition. So this is my function c of xt, and I want to solve dx dt equals x of 0 equals some initial condition x naught. Well, if dx dt equals x, we know from calculus 1 or 2, what's the only function whose derivative is equal to itself? It's x of t equals e to the t, and when t is 0, it has the value x0. So this is the characteristic curve. And we can check, well, then maybe I'll just do it. So if I look at the solution of the differential equation defined on this curve, x of t comma t, and I differentiate this with respect to t, I get the partial of u with respect to x, the x dt, or let me differentiate first with respect to t. So this is the partial of u with respect to t, dt dt, plus the partial of u with respect to x, dx dt. This is u sub t times 1 plus u sub x, and dx dt is equal to x. So this is ut plus x u sub x. That's supposed to equal e to the t. So u of xt is the integral of e to the, let's say e to the tau d tau from 0 to t, right? If the derivative of u is e to the t, then u of xt is equal to this integral, and u of x0 plus x0, right? Because u of x comma 0 is 0 plus x naught. Sorry. I mean, that's what it is, but so u of xt is if this plus u of x0. The integral of e to the tau, d tau, this is e to the t minus 1 plus, what is u of x0? That's f of x0. That's f of 0. Let me write this down more carefully. So the derivative of this function is e to the t. So u of x of t comma t is the integral of this plus the value of this at 0. U of x of 0 comma 0. U of x of 0 comma 0. So this is e to the t minus 1 plus f of x of 0. X of 0 is x naught. So u of x of t comma t is e to the t minus 1 plus f of x naught. What is x naught? It's f evaluated at x e to the minus t. So we've solved the problem. U of xt is f of x e to the minus t plus e to the t minus 1. Well, I don't know. Maybe it's not right. Oops. I'm sorry. I forgot to start the recording. So I'm going to start the recording and review a little bit of what we've done so far. Okay. So let's just review. There are three methods of solving partial differential equations that I want to make sure I cover before the next exam. Separation of variables, we did that a tiny bit. The method of characteristics, which is what I'm talking about now, and Laplace Transform, which hopefully I'll get to start today, if not next week. The method of characteristics we're going to use to deal with a Cauchy problem. So a Cauchy problem in PDE is a problem where you have a partial differential equation with some initial condition and no boundary condition. So for us, this is going to be a first order PDE in the variables x and t, linear. So it's going to look like the partial of u with respect to t plus some function of x and t partial u with respect to x equals some f of xt with an initial condition that u of x naught, u of x at time 0 is some function f of x. And the simplest case is when this function is just a constant, just a number, and it's homogeneous. U of xt plus cu partial u with respect to t, c partial u with respect to x equals 0. And we can just check, really by inspection, that if we take our initial condition, f of x, this is capital here, capital F, and I look at the function f evaluated at x minus ct, this is a function defined for all x. Because we're always considering x from minus infinity to plus infinity and t greater than or equal to 0. So f of x minus ct is well defined, and you check by differentiating that this is in fact the solution of this equation. So that's pretty easy. These are so-called traveling waves. So let's start to solve some problems. This is just, again, I'm just reviewing what I did a moment ago. Suppose we have ut plus xt times partial u with respect to x equals 0 and some initial condition. So you look at the ordinary differential equation. Right? So one reason why you have to know ODE to solve PDE is we often reduce a partial differential equation to an ordinary one. This is dx dt equals xt. Separation of variables works. We get x is equal to x naught e to the half t squared. So this is a curve in the plane. It's a curve that looks like that. And on this curve, the function u is constant. Right? How do we know that? Well, we can prove it in general, but in particular, you just compute d of derivative with respect to t, time, of u of x of t comma t, and you get 0. So this is constant. If it's constant, that means it has the same value everywhere. In particular, it has the same value when t equals 0. So u of x of t comma t for every time is u of x of 0 comma 0, which is just the initial condition, f of x naught. X naught is x e to the minus t squared over 2. So f of x e to the minus t squared over 2 solves the differential equation. Let me just check this, just so we see that it's really true. So u of xt is f of x e to the minus t squared over 2. So the partial of u with respect to t is holding x constant, this is f prime of x e to the minus t squared over 2 times the derivative of this with respect to t is x minus t e to the minus t squared over 2. And the partial of u with respect to x is f prime of x e to the minus t squared over 2 times the derivative of this with respect to x, which is e to the minus t squared over 2. So if you take u sub t and you add xt times this plus this cancels, equals 0. ut plus xt ux equals 0. So it checks. So it worked. Next was an inhomogeneous partial differential equation. ut plus x u sub x plus on the right-hand side, instead of 0, an e to the t. So again, we look for the characteristic curve, which is what you get when you solve dx dt equals whatever is multiplying u sub x. Dx dt equals x, that's just e to the t. And the value at 0 we call x naught. So if you look at u of x of t comma t, and you differentiate with respect to t, you get this plus this, which is e to the t. So the derivative of this function is e to the t. By the fundamental theorem of calculus, the antiderivative is the integral from 0 to t plus the value of the function is 0. The value of the function u of x of 0 comma 0, that's just the initial condition. Now the integral of e to the t from 0 to t is e to the t minus 1 plus f of x of 0. x0 is x e to the minus t. So we got this solution. Let's check if it's correct. So the partial of u with respect to t, if I differentiate this with respect to t, I get f prime evaluated at x e to the minus t times the derivative with respect to t of x e to the minus t, which is minus x e to the minus t. Differentiate this with respect to t, I get e to the t. Differentiate this, I get 0. So that's u sub t. What is u sub x? If I differentiate this with respect to x, I get f prime of x e to the minus t times the derivative of this with respect to x, which is e to the minus t. I differentiate this with respect to t, I get 0. So this is what it is. Suppose I multiply this by x, and then I add u sub t plus x u sub x. These cancel, I get e to the t. That's my differential equation. ut plus x ux equal e to the t. So it checks. What about the initial condition? U of x comma 0 is what? When t is 0, I get f of x e to the 0 is 1. E to the 0 is 1 minus 1. They cancel. I get f of x. So the initial condition also is satisfied. All right, well, let's do some more. I mean, I really want to concentrate on actually solving problems. So I had also assigned problem 6, which is really 5 problems. It's A through E. So let's take a look at them. See how many we can do. So problem 6A. We have the differential equation, partial of u with respect to t plus x, partial of u with respect to x, is minus t times u. And the initial condition, u of x0, is f of x. So this is my function multiplying u sub x. That's my c of xt. I need to, my curve is the curve you get by dx dt equals x. X of 0 equals some number that I'll call x naught. Dx dt equals x means let me check something. Yep. Dx dt equals x. So x of t, if dx dt is x, that's some constant times e to the t. And the constant is just the value x of 0, with x at times 0, which I'm calling x naught. So if I take u of x of t, comma t, and differentiate it with respect to t, as again, by the chain rule, this is the partial of u with respect to t, du dt, sorry, dx dt, plus the partial of u, sorry, partial of u with respect to x, dx dt, plus the partial of u with respect to t, dt dt. Dx dt is equal to x. So this is x, u sub x plus u sub t. That's exactly minus t times u. So if we look at this function, the solution of the equation along this curve, right? This is my curve. On that curve, du dt is equal to minus tu. In other words, du dt equals minus tu. This is a separable ordinary differential equation. 1 over u du dt equals minus t. So the integral of 1 over u du is the integral of minus t dt. This is log of u equals minus a half t squared plus some constant. So u is equal to e to the minus a half t squared times some constant. This is u of x of t, comma t. U of x of 0, comma 0 is c e to the minus 1/2 times 0. This is c. This is just the initial condition, f of 0. Sorry, yeah, f of 0. Sorry, f of x0. x0 is x e to the minus t. Everybody's so quiet. So let me just go back and look at this again. So this is my differential equation. It's first order. They're only first derivatives. Partial of u with respect to t, partial of u with respect to x. It's ut plus something times u sub x, some function, equals, it's not homogeneous, it's minus t times u. And this is my initial condition, u of x comma 0 is f of x. So the first thing I do is solve the differential equation, dx dt equals x. Right? This is the function. I have to solve dx dt equal to whatever that is. But this is just the simplest differential equation in the universe. The solution is x naught e to the t, where x naught is the value of x at time 0. If I look at u evaluated along this curve, x of t comma t, I differentiate that with respect to t, I get minus t times u. So u of x of t comma t is you take the antiderivative or the integral. So, so du dt is minus tu. That's a differential equation which is separable, right? I have two differential equations. First this one, now this one. This is log u equals minus t squared over 2. So u is some constant times e to the minus a half t squared, e to the minus t squared over 2. What is c? C is u of x of 0 comma 0, which is f at the time x naught. X naught is x e to the minus t. So that's what my c is. So what I get as my solution is u of x comma t is c f of x e to the minus t times e to the minus t squared over 2. So for this differential equation, I claim this is the solution. So you might do the following right now. Take a piece of paper, take the partial of u with respect to t, take the partial of u with respect to x, plug it into this equation, and see if it really is the solution. That is what you should do. So check it out, see if it works. I'll check it, see what happens. Partial of u with respect to t, by the product rule, this is f prime of x e to the minus t times the derivative of x e to the minus t. So partial, all right, times the derivative of x e to the minus t, which is minus x e to the minus t times the second term, plus f of x e to the minus t times the derivative of this, which is minus t e to the minus t squared over 2, partial of u with respect to x is f prime of x e to the minus t times e to the minus t times e to the minus t squared over 2. This is just the product rule, plus yeah, that's all it is. You differentiate this with respect to x, It's e to the minus t squared over 2, f prime of this, times e to the minus t. If I multiply this by x, what happens? This term and this term, they only differ with this minus sign. They cancel. So this plus this is equal to this. So u sub t plus x u sub x equals this. This is minus t, and this times this, that's my u. See that? So my differential equation is satisfied. Ut plus xux is minus tu. Well, let's try another one. So we did 6a, we did 6b, so I guess we should try 6c. So 6c is the following partial differential equation. T u sub t plus x u sub x equals minus 2u u of x0 equals f of x. I just noticed something because I was, oh, sorry. I think I just did 6a. So now I should be doing 6b. So 6b is the differential equation t u sub t plus x u sub x equals minus 2u. And again, this is for all x from minus infinity to plus infinity. But in this case, it's for t greater than 1. So the initial condition is at time 1. U of x at time 1 is some function at x. So there are two things about this equation which are different from the three we did previously. One is that we're not starting at t equals 0. We're starting at t greater than 1. And the coefficient of u sub t isn't 1. It's t. Well, I'd rather have the coefficient be equal to 1 here. And since t is greater than or equal to 1, I can divide by t. It's not 0. So I can just rewrite this as u sub t plus x over t times ux equals minus 2 u over t. So dividing by t, this is now the form of my differential equation. And the first ODE I need to solve to find the characteristic curves is dx dt equals x over t. So this means we can separate variables. 1 over x dx dt equals 1 over t. So the integral of 1 over x is the integral of 1 over t, this is log x, equals log t plus a constant. So if you exponentiate, you get x equals some constant times t. And let's say the initial value, so at t equal to 1, let's just let x of 1 be equal to x of 1. So my curve is x of t equals x1 times t. And along that curve, the derivative with respect to t of u of x of t comma t is going to be equal to minus 2u over t. So I have another ordinary differential equation. Du dt equals minus 2u over t. Again, this is another separable ordinary differential equation. I get 1 over u du equals minus 1 over t dt, integrate. So log u oops, I'm sorry, it's minus 2u over t. So I forgot this 2. So this is minus 2 over t. So log u equals minus 2 log t plus some constant. So u equals t to the minus 2 times the constant. So u equals, so this is the same as log of t to the minus 2, 1 over t squared plus a constant. So u equals some constant over t squared. So u of x of t comma t is a constant over t squared. What is the constant? U at x of 1 comma 1 is, so this is u of x1 comma 1. This is just my initial condition. This is f of x1. Equals c over 1. C is equal to f of x1. So u of x of t comma t is c over t squared is f of x1 over t squared. X1 is x over t. Times 1 over t squared. So we started with this differential equation. We can divide by t, because we're only considering positive values of t. So the differential equation looks like this. dx dt equal x over t gives us the characteristic curve. Along that curve, the derivative is equal to the right-hand side. The solution of this differential equation is just constant times t. And the constant is x1, the value of the initial condition at t equal 1. And you work your way through, and this is the solution. And if you check, you'll see that it works. Let me do just one more, and then I want to turn to the Laplace transform. So this is 6c. Here we have the differential equation u sub t plus u sub x equals minus t u, and the initial condition u of x0 equals f of x. So here the coefficient of u sub x is 1. We're just solving dx dt equals 1, which means x of t, when you integrate 1, you just get t plus a constant. And the constant is just the value of the function at 0, which we'll call x0. So if we take u of x of t comma t and differentiate with respect to t, we will get minus tu, or du dt is minus tu. This is separable. 1 over u du dt is minus t. So when we integrate, we get that the log of u is the integral of minus t dt is minus t squared plus a constant. So u, which is u of x of t comma t, is some constant times e to the minus, when you integrate t, you get minus a half t squared. Should you get that right? When t is 0, this is my x0. x0 is x minus t. So I get u is equal to x naught, x minus t, e to the minus t squared over 2. Let's just check. Here's my function u. Partial of u with respect to t is the derivative of this with respect to t, which is minus 1 times e to the minus t squared over 2, plus x minus t times the derivative of this with respect to t, which gives me a minus t e to the minus t squared over 2. So this is e to the minus t squared over 2 times what? I have minus 1 minus tx plus t squared. That's what it seems to be. If I differentiate this function with respect to x, I just get e to the minus t squared over 2. If I add them, u sub t plus u sub x, these cancel. I just get this. Minus t times x minus t e to the minus t squared over 2. But this is u equals minus t times u. And that's what it's supposed to be. That's the differential equation. So this checks. I'll do some more of these problems next week because there still are quite a few more to do. But I want to introduce the Laplace transform. So back in first year calculus, you learned something about improper integrals. So you could have an integral from 0 to infinity of some function f of t dt, and this was defined as see, why is it improper? Because it's an infinite integral of integration. You define integrals over finite intervals, like an integral from 0 to b of f of t dt. So you take the integral from 0 to some positive number b, calculate this integral if you can, and take the limit as b goes to infinity. And this is the definition of this kind of infinite improper integral. It doesn't necessarily exist, but if it does, you found it. So for example, suppose I take the function f of, suppose I take the integral of from 0 to infinity, e to the minus some number s, I'll take 2, e to the minus 2t dt. So this would be the limit as b goes to infinity, the integral from 0 to b, e to the minus 2d dt. So we need to calculate this. Well, the integral of e to the minus 2d dt is minus a half e to the minus 2t, right? This is the antiderivative. If you evaluate this from 0 to b, I get minus 1/2 e to the minus 2b minus this evaluated at 0. At 0, this is 1. So I get a half minus that. That's what this finite integral is. So the integral from 0 to infinity, e to the minus 2d dt, is equal to the limit as b goes to infinity of this integral, which is a half minus 1/2 e to the minus 2b. As b goes to infinity, this is just a half, and this is just decaying to 0. So the answer is a half. This improper integral equals a half. And if we change this constant to some number c, actually I'll change it to some number s. So e to the minus st, the integral of e to the minus st is minus 1 over s, e to the minus st. So that's 1 over s, 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 s. So that's just a slightly more general result, but within first year calculus, the integral from 0 to infinity of e to the minus st dt is 1 over s for s greater than 0. If s weren't greater than 0, the integral wouldn't converge. Let's try another one. Suppose I take the integral from 0 to infinity of t e to the minus s. So s is just some constant. T e to the minus st dt. So this is the limit. So let's just say fix a constant s greater than 0. The limit as b goes to infinity, the integral from 0 to b of t e to the minus st dt. How do we do this? Well, I don't know, integration by parts. If I put t here and e to the minus st here, the derivative of t is 1, and the antiderivative of this is minus 1 over s e to the minus st. So the integral from 0 to b, t e to the minus st dt, is this times this, minus t over s e to the minus st, evaluated from 0 to b, minus the integral of minus 1 over s e to the minus st dt from 0 to b. Okay. So stop me if you have any questions. I mean, this is calculus, but you have no calculus. So when t is equal to b, this is minus b over s e to the minus bt. And when t is equal to 0, this is 1. And this is 0, right? When t is equal to 0, this is 0. So it's just minus b over s e to the minus bt. And this is plus 1 over s. The integral of e to the minus st is minus 1 over s e to the minus st, evaluated from 0 to b. So this is minus b over s e to the minus bt. Oops, I forgot something. What did I forget? No. When t is equal to b, this is minus sb minus sb. And this is minus 1 over s squared e to the minus sb minus, when t is 0, 1. And what happens to this as b goes to infinity? Well, b over e to the sb goes to 0. This goes to 0. This goes to 1 over s squared. So if I did my calculus correctly, this says that the integral from 0 to infinity of t e to the minus s over t dt is 1 over s squared. Okay, so what I've just done are two examples of the Laplace transform. So the Laplace transform of a function u of t is the integral from 0 to infinity u of t e to the minus st dt. And this depends on this parameter s. So this is really a new function, which I'll call L of s, u of s. or I can also call it as the Laplace transform LU of S. These are just two commonly used notations for the Laplace transform, if it exists, right? Improper integrals don't always exist. So you have to know what conditions on a function will guarantee that this integral exists. So the simplest condition is, so we say u of t has exponential growth, exponential order, if the absolute value of u of t is less than or equal to c times e to the at for some c greater than 0, a greater than 0, and t large enough, not necessarily greater than 0, but from t greater than or equal to t naught. So a function u, which in absolute value is bounded by an exponential function e to the at for all t from some point on, is said to have exponential order. And we can make the following observation. If I take u of t e to the minus st, and I take the absolute value of that, that's the absolute value of u of t times e to the minus st. Note. Because the absolute value of a product is the product of the absolute values, but the exponential function is always positive. So the absolute value of this is just itself. We're assuming u of t satisfies a condition like this. So this is less than c e to the at e to the minus st, which is c, using our rules for exponents, this is c e to the minus s minus a times t. And the integral of c e to the minus s minus a t dt convert from, let's say, from t naught to infinity, converges if s is greater than a. If s is greater than a, this is a positive constant, this integral converges. So if u of t has exponential order, then the integral of u of t e to the minus st dt, that's the Laplace transform, that's less than or equal, the integral of a function is less than or equal to the integral of the absolute value of the function. This we just saw is bounded by c e to the minus s minus at, at least from some number on. That's all that's important. And this converges. So if you have learned a little bit of analysis, you know that if an integral converges absolutely, it converges, and this integral converges absolutely. So we've already seen two Laplace transforms. If we take the function u of t equals 1, the Laplace transform of 1, which was the integral from 0, integral from 0 to infinity 1 e to the minus st dt. What was that? integrating 1, that's what this is 1 over s. Laplace transform of the function t, that's the integral from 0 to infinity, t e to the minus st over 2 dt. We calculated that a moment ago. We got 1 over s squared. These are all functions of s. Suppose I take the Laplace transform of the nth power of t. That's the integral from 0 to infinity, t to the n e to the minus st dt. Well, you can work that out. This is for n, a positive integer. This is n factorial over s to the n plus 1. Notice if n equals 1, that's this case, 1 factorial is 1, and 1 plus 1 is 2. And I remind you that n factorial, this is the product of the positive integers up to n. 0 factorial is defined to be 1. So this is the factorial function. So n factorial is just the product of the positive integers from 1 to n. This is defined for all s greater than 0. Let's see. Suppose I take the exponential function. Suppose I take u of t to be e to the at for some number a. Let me try and calculate the Laplace transform of e to the at. That'll be the integral from 0 to infinity, e to the at, e to the minus st dt. This is the integral from 0 to infinity, e to the minus s minus at dt. So this converges. Well, sorry. So this integral converges so long as s minus a is positive. So this converges for s minus a greater than 0 or s greater than a. And can we calculate that? So well, let me just go back to the definition. This is the limit as b goes to infinity, the integral from 0 to b, e to the minus s minus at dt. So let me calculate this. The integral from 0 to b of e to the minus s minus at dt is minus 1 over s minus a, e to the minus s minus at, evaluated from 0 to b. So when t is equal to b, I get e to the minus s minus a times b over s minus a. When t is 0, I get minus this evaluated at 0, I get 1 over s minus a. And what is the limit of this as b goes to infinity? Because that's what I plug in here. This goes to 0, I'm left with 1 over s minus a. So I have that for a greater than s, the Laplace transform of e to the at is 1 over s minus a. So you might be asking, this is very nice calculus, but why do we need it in differential equations? Well, it's because the Laplace transform of the derivative of a function is really very beautiful. Let me try and calculate this. So suppose I have the function u prime of t. U is a function, and I differentiate it. And I want to find the Laplace transform of u prime. So this is the integral from 0 to infinity, u prime of t, e to the minus st dt, which is limit, as b goes to infinity, integral from 0 to b of u prime of t, e to the minus st dt. So again, let me use integration by parts. I'll put e to the minus st there and u prime there. So here I put the derivative with respect to t, minus s e to the minus t. And here, the antiderivative of the derivative is u of t. So the integral from 0 to b of u prime of t, e to the minus st dt, is this times this, u of t, e to the minus st, evaluated from 0 to b, minus the integral of this times this, minus times minus makes this a plus s, u of t, e to the minus st dt, from 0 to b. What is this? This is u of b e to the minus sb minus u of 0. That t equals 0. This is just 1 minus u of 0 plus this integral. And if my function u of b has this exponential order, let's see. So let's just make a note. If u of t in absolute value is less than c e to the at for t big enough, then u of b e to the minus sb in absolute value is less than c e to the bt e to the minus sb. That's c e to the minus s minus t times b. U of t less than c e to the at. So u of b e to the minus sb is less than or equal to, when t is equal to b, this is c e to the ab e to the minus sb. So this is c to the minus s minus a times b. And if s is bigger than a, this goes to 0 as b goes to infinity. So this term goes to 0 for s bigger than a. And as b goes to infinity, this is just the Laplace transform. So what we have is the Laplace transform of u prime is equal to s times the Laplace transform of u minus u of 0. So what you'll see what the Laplace transform is going to do is to convert a differential equation to a polynomial, to an algebraic equation. The derivative of the Laplace transform of a derivative is just the Laplace transform of the function times s minus this initial condition. So let's see what we can derive from that. So let me just repeat this. The Laplace transform of u prime is s times the Laplace transform of u minus u of 0. Suppose I take the second derivative, u double prime. The Laplace transform of the second derivative, this is like the Laplace transform of the derivative of the derivative. So this is equal to s times the Laplace transform of u prime minus u prime at 0. But L of u prime is equal to this. This is s times L of u minus u of 0 minus u prime of 0. So that's s L of u minus s u of 0 minus u prime of 0. So these are two basic equations. And all we're using is basically some simple integration by parts. Consider the following ordinary differential equation. So u is just a function of t. And u double prime plus u equals 0 for t greater than 0 with the initial conditions u of 0 equals 0, u prime of 0 equals 1. Let's take the Laplace transform of this. The Laplace transform of u double prime plus u, well, this is a linear operator. This is the Laplace transform of u double prime plus the Laplace transform of u. And let me write L of u of s. It's just the function capital U of s. This equals the Laplace transform of 0, which is 0. Oops, sorry. Yeah, well, that's right. But the Laplace transform of u double prime, it's equal to this. It's equal to s, capital U of s, that's this, minus little s u of 0 minus u prime of 0. This is 0 and this is 1, so this is s u of s minus 1. So what I get, this plus this equals 0. That says that s u of s minus 1 plus u of s equals 0. In other words, s plus 1 capital U of s equals 1, or u of s, the Laplace transform of the solution of the equation. Oops, let's see. I did something wrong here. L of u prime was SL of U minus this. So this is S squared minus S minus 1. That's right. So U of S is equal to 1 over 1 plus S squared. This is the Laplace transform of U. So the solution of this differential equation, U, has the property that its Laplace transform is equal to 1 over 1 plus S squared. And I'll show next time that the only function whose Laplace transform is 1 over 1 plus S squared is U equal to the sine of t. And you know from that that's the solution. Sine of 0 is 0, cosine of 0 is 1. So let me just say, what I'm doing is in the book by Logan. And there's a discussion of Laplace transforms starting on page 106. And I'm putting in a few more details than he, but this is really quite important in mathematical applications and in mathematics and physics and many other places. Laplace transform is a basic technique. And when you apply the Laplace transform to an ordinary differential equation, you get a polynomial to solve. When you apply it to a partial differential equation, it reduces it to an ordinary differential equation. So in ODE, you get an algebraic equation from an ordinary differential equation from the Laplace transform. In PDE, the Laplace transform takes away a derivative basically and leaves you just an ordinary differential equation to solve. So long as you can solve the ordinary differential equation, you're in good shape. Okay, that is where we are for this week. So everybody stay well. And really, in this book of Logan, you should go to page 106 and start to study the section on the Laplace transform. That's the key. No, I'm not taking attendance today. Sometimes I do. I figure some people stayed up all night watching the election returns, and